Hi everyone, so we're going to look at 26.8 today, which is about decay modes. So if you were in school, I did this lesson with you. If you weren't in school, then this video should help. So the first thing to look at is this thing called the NZ graph. Have a look on the left. Up the left hand side, we've got N as the number of neutrons. So these are the number of neutrons present in an atom. And then you've got Z along the bottom, which is the number of protons. So NZ graph is a graph showing how the number of protons, if you increase the number of protons, what happens to the number of neutrons. And here you can see this black straight line. This is where N equals Z. So if you see here, 82 protons equals 82 neutrons, and so on. And what you can see, this black line is the atoms plotted. So the elements in the periodic table have been plotted. And as you can see, as they get bigger, they move away from the proton, from this line, which meaning that they have more neutrons than protons. Okay. So we're going to have a look at that now. The idea is that this black line here is stable. So these nuclei would be stable. So everything's trying to get to the black line. Okay. So if you're going to plot this graph, or just asked to describe this graph, the first 20 elements, so the light isotopes, their N equals Z, so they follow this straight part here. Okay. So up to about calcium. At calcium, they start to veer off the stable elements. So at Z equals 20 plus, the stable nuclei have more neutrons than protons. This helps bind together the nucleons with no extra repulsive electrostatic force, i.e. if you have more protons, the the amount of force trying to push the nucleus apart increases, and so a way to overcome that is to have more neutrons. At Z plus 60, you begin to get alpha emitters, and you get the most alpha emitters at Z 80 plus, and N equals 120. So you need to try and remember those numbers. So if you look at this graph, the alpha emitters are these yellow ones. So what happens, say you've got this element here. To try and become stable, it's going to lose protons and neutrons. So it will start to move like this across. And then it might do some more decays here. You can see it's moving to beta plus to try and get to this black line. You need to remember these numbers. It will ask you to quote them, okay? Beta minus decay, they're on the left of the stable nuclei, so they're here. So they're neutron rich. They become more stable by converting a neutron into a proton. So they lose a neutron and increase a proton. So this element here, lose a neutron, increase a proton, lose a neutron, increase a proton, lose a neutron, increase a proton, lose a neutron, increase a proton. So they get to the stable black line. Beta plus decay, they're on the right hand side, so they're proton rich, so they lose a proton and gain a neutron. So they will do this. So this element here, lose a proton, gain a neutron, lose a proton, gain a neutron, lose a proton, gain a neutron, lose a proton, gain a neutron. And then they'll hit this line here. Okay. So that's the NZ graph. There's an example question on it in the exam questions. You might get asked to draw the NZ changes in a nuclear decay. So if we look at this, so that's an example there. So if we look at this, an alpha, number of neutrons increasing up here, number of protons increasing this way. So in an alpha decay, you lose two neutrons initially. So you go down 2. And you also lose 2 protons, so you go this way. Alright? In beta minus decay, a neutron turns into a proton, so you lose a neutron, gain a proton. And in beta plus decay, you turn a proton into a neutron, so you lose a proton, gain a neutron. So that's what these arrows represent. Here's an example. This is the NZ changes for uranium decay. So we start with 23892. 23892 is going to give out an alpha, okay? So we're going to end up with thorium 90, and then it's got 144 neutrons. So then I'm going to give out another alpha. Okay, so we plot that by drawing 2 down and 2 across, and then we're here, and that's radium 23888. Then it undergoes another decay where it gives out beta minus. So in beta minus, you turn a neutron into a proton. So here, you lose a neutron, gain a proton. Then it undergoes another beta decay to turn back into an isotope of thorium, different isotope this time because it's got less neutrons. So again, lose a neutron, gain a proton. And then it undergoes alpha decay. Again, okay, and we're going to end up with 88. So with another radium, so these are the same element, it just has less neutrons. So this shows a process of decay that the unstable 23892 uranium can go through to try and get stable. And what it's doing is it's trying to move, basically on this graph, by a series of processes. It's trying to move from here down here to try and get to this line. That's what it's trying to do. Okay. Just be careful because there sometimes questions will start here and ask you to work backwards to get to the start, so the original nuclei, especially in multiple choice questions. So just keep a real eye out for that. Are you asked to find the product, in which case it's here, the radium, or are you asked to find the original nuclei and work backwards, which in this case is uranium? Just want to talk one last thing about nuclear energy levels. So after an unstable nucleus emits an alpha or beta particle or undergoes electron capture, so on this graph as well, you've also got electron capture, okay, and you've also got fission. So that nucleus might still have some excess energy, in which case, if it has some excess energy, it might emit a gamma photon. So excess energy is like when we did electron energy levels in particles, the nucleus itself can have energy levels the same as an electron has energy levels. So if a daughter nucleus is produced in a reaction, in a nuclear reaction here, like this radium, if that radium daughter nucleus is still in an excited state, then it can release a gamma photon. And the excited state is short-lived, and the nuclei will move into its ground state as soon as possible. This is an example image here. Just move me out of the way. So this magnesium, okay, has become this aluminium. It's in an excited state here. So it could give out a gamma photon here and jump all the way down to its ground state, or it could give out two, one here and one here. And the one that with the most energy is the biggest jump. So this is the biggest gamma ray photon, okay? So this gamma ray, this jump 1, would have an energy of 1.02 mega electron volts, because you're going from 1.02 to 0. This one would have the difference between these two, and then this jump is 0.83 mega electron volts. So you treat those the same way as you would treat excited energy levels in electrons. So that's me just explaining that process there. Okay. It's trying to move me around. There you go. So I'm not in the way. Last thing you need to know about, it's not terribly exciting. However, it is incredibly important for people who need it, is the technetium generator. So it's used in hospitals as a gamma source. You have this technetium 99 and it stays in an excited state long enough to be separated from its parent isotope, which is the metastable technetium. So the difference between these two, they're both technetium, they're both the same isotope. It's just this one is at a higher energy level than this one. This is the stable one, so it's in its ground state. And because it's in this excited state, you can remove it from its parent isotope, and it's going to emit gamma, which is helpful because you can use gamma to do different things. This is how you produce it. So you've got this MO 99, I think that's molybdenum 9942, and it decays by beta minus into this technetium, okay, and it has a half-life of 67 hours. And the second reaction, okay, this is where you're giving out your gamma, that lasts for about 6 hours. And then when you give out the gamma, this technetium will then decay by beta minus into rubidium, and it has a half-life of 500,000 years. So this is really important. This means you can make your product, store it for 67 hours, remove the part that's going to produce gamma, give it to your patient, and over a 6-hour window it will be producing gamma. And then anything that's left inside the body will have a half-life of 500,000 years. So it will stay a long time in the body, but it's not very active. So it's not producing a lot of gamma. And so the background radiation is probably higher than the dose they're receiving from the technetium. And here you go. This is how they do it. They use sodium chloride, and then they have this tube here to do it. But you don't need to know about this. It's in the book if you want some more information. So the ammonium molybdenite, which is this, is exposed to neutrons for several days to make the isotopes unstable. Then sodium chloride is added to remove the parent, and then sorry, I think I've got this wrong at the start. This one, the metastable one, that's the excited one, and this is the normal one. So this one, the excited one, that's the one that's going to give out gamma and then become the normal one here. I said that wrong at the start. And then this one will then decay by beta, but very, very slowly. So the sodium chloride is added to remove the parent nuclei, which leaves behind this excited state, technetium. And then you give it to the patient. And it's used to monitor blood flow in the brain, and it's used with a gamma camera to image internal organs. So that's gamma camera is used in PET scans, positron emission tomography. Okay. Here are the questions for you to have a go at. They're on the PowerPoint on the virtual classroom if you want them. I will do a video showing you how to do the answers for those of you who need them, but obviously the answers are in the back of the book. Okay, see you later. Thank you. Bye.